Baking theory. In this chapter, we will go over some concepts behind the baking process, a pipeline example, and tips to achieve a clean bake. Baking is the last step before texturing. This is the real test of everything we have done so far, where high poly, low poly, and UVs come together to transfer the high resolution details from the first to the second. We can bake with many different tools: Substance Painter, XNormal, Blender, 3ds Max. But the most comprehensive baking software out there is Marmoset Toolbag. It is fast, easy, convenient, and extremely customizable, so we can always get what we want, the way we want it. It actually works so well that it can be a bit dangerous. Game engines are generally more quirky and finicky, and bakes that look great in Marmoset may not look as good in the engine. For this reason, we must always test our bakes in their final environment. Unfortunately, some modeling or UV mapping mistakes only become apparent after baking, so this is the phase where we will make the most fixes and corrections, going back to all the previous stages. This means we must be extremely observant, examining the final result with a critical eye under different conditions to make sure no error gets past us. Redoing work might seem crushing at first, but it happens a lot in game dev. We need time to make sure things are done right, especially when we don't have much experience yet as a professional. Sometimes I spot a baking error in the middle of texturing, and I have to go back and fix it, redo the bake, and then reload the maps and meshes back into Painter, while crossing my fingers, hoping that my texturing work so far has been preserved. This is also why procedural texturing using masks and generators is way more efficient than trying to paint everything by hand. It's easier to reset, redo, or even apply to a completely different mesh, should we need to. Baking groups are pieces that are baked together. Normally, only a single low poly is baked per group, with high and low resolution meshes. However, it's normal to have several meshes in the high poly folder that we then simplify to a single low poly mesh to save on unnecessary geometry, like screws, paneling, or smaller pieces. Being very organized is key to a good fast bake. The quickest way to create baking groups is to import them automatically to Marmoset, and for that we need a rock-solid naming convention that saves us work every time we need to export new mesh iterations when fixing baking errors. Traditionally, each weapon or prop will have their own texture set. That would be at least one, but usually more, due to interchangeable modular parts or attachments. We will follow this modular workflow for our revolver, splitting it in 3 texture sets. First, the common pieces: cylinder, frame, trigger, etc. The bullet could go separately in its own texture set to accommodate possible changes in ammo types. But here, for the sake of simplicity, we will bake them alongside the other common pieces. Then we have the parts of the Mark I revolver: barrel 1, grip 1, and hammer 1. Alternatively, when we want a Mark II revolver, we will use a third set, including barrel 2, grip 2, and hammer 2. All of these final textures will be 2K, so they will be baked in 4K. Now, let's follow the baking process step by step. After the UV unwrapping stage, we should verify our pieces, check them for errors, and apply mesh transformations. We start with a quick, non-optimized initial packing that we will use for a bake test. Keep in mind that even if the packing is not final, the unwrapping and alignment of the UV shells must be. Check your packing settings to avoid breaking it by rotating the shells automatically. Create and assign materials to the meshes if they don't have them yet. Their names and the meshes assigned to them will be each of the texture sets. Also, add a high poly material to the high poly meshes so we can tweak their parameters in Marmoset. Then we configure the baking groups inside Blender by naming the corresponding high poly and low poly pieces, but ending in the suffixes _high or _low. This way we avoid having to reconfigure baking groups inside Marmoset every time we export our meshes, which, believe me, will save us a lot of time. Even cage sizes should stay consistent between exports. After naming, export high poly and low poly separately and use Marmoset's autoload function to automatically create the groups. Meshes should be exported triangulated, but make sure shading stays consistent, whether we use a triangulate modifier or we do it on export. Check that your planar faces are actually planar to avoid shading gradients. Run a quick bake test with low samples and final or half resolution to check for errors in the meshes, cages, unwrapping, or bake group configuration. Once the bake test looks clean, we do the final, very optimized UV packing. It's good practice to let UV Pack Master run for a while to determine the best placement for our shells. We move the mirrored shells 1 unit outside the UV space, so they are not baked over each other, which can result in baking artifacts. This will also make mirrored parts easier to identify, since it is not very easy to spot stacked UV shells at a glance, depending on which 3D package we are on. Definitely not in Blender. Once the bake is final and we export to Painter for texturing though, we can move them back in the UV space, or we won't be able to paint on them. We do the final bake at double resolution, and check again for errors before committing to the result. It's a good idea to have non-metal material to check the ambient occlusion bake, and then add metalness to better see the final normal map shading. Roughness should stay in the medium to low numbers, around 0.3. To remove the baking's inherent distortion, also called skewing, we can take 2 paths. The first is skew painting directly in Marmoset. This is a good solution for simple pieces without that many details baked flat. The brush is not very precise or easy to control. The second option, and more old-school method, is image compositing with good old Photoshop, or an equivalent image processing software. We make a mix between a bake with a smooth cage and one without it, using masks. The smooth cage bake will look good overall, but the details that are baked in the interior of flat faces will appear skewed. We mask and replace those with the ones baked without a cage to remove the skewing. We can also take the opportunity to fix annoying baking shortcomings, like cylinder waviness, or errors where the cage is too extreme or clips with itself. After that rundown of the baking pipeline, let's discuss some tips and tricks. Shading issues from the high poly, like pinching, will transfer to the low poly during the baking process. Double check both stages of the piece, not just the low poly. Remember to remove all sharp edges from high poly to avoid faceting. Use a fair amount of geometry for baking. Big shape differences between high and low poly models will result in a poor bake. We can also simplify or tweak the shape of the high poly pieces in order to have a less complex low poly. Always think 2 steps ahead and foresee possible issues. We can go back to any part of the pipeline at this stage, so don't be stuck to a bad high poly and deal with issues that can be avoided just by changing it. Run the test bake in the final expected resolution, or even better, at half resolution. This makes it way easier to spot baking errors. A bake in 4K will almost always look good, because some errors can be compensated by sheer amount of resolution. It is also faster for the computer to do repeated bakes at a smaller resolution, although this is almost negligible now with Marmoset Toolbox 4 high baking speed. The test bake must have the final unwrapping, but the final packing is not necessary. When testing, we need to check the unwrap, modeling, and shading. Since changing the low poly often implies changing the UVs, it's best to make sure everything is okay before devoting time to packing, even when it's automated. When we identify a baking error, we should make a note about where exactly it is located, so we don't get tied up fixing other stuff and forget about it. Baking is the most destructive step of our whole workflow, and errors here imply redoing many steps, so we must be extremely rigorous with our QA observations. For each error, we investigate which stage is affected. Is the error present in the high poly already, low poly, UVs, or just in the normal map? After that, we make our fixes, export everything again, rebake, and check again. Since these steps take time, the best way to go is collect all the errors and then fix them all at once, to avoid repeating operations unnecessarily. The final bake should be at double resolution than the planned textures, and use 16-bit color depth for normal maps. This will reduce the quality loss of exported textures, since we will have a lossless source file to compress and dither. There are two ways to bake a correct ambient occlusion map for animated pieces. We can uncheck Ignore Groups in the AO baking options, which is on by default. This will make it so pieces will not affect each other when calculating occlusion, resulting in a more plain AO map, but one that keeps being correct when pieces move from their original position. We can also separate moving part clusters to bake a proper AO, but this process is a bit more slow and involved. It requires exploding both the high and low poly meshes for baking, so they don't affect each other while baking the occlusion, and thus result in artifacts once pieces move from the original position in which they were baked. Preparing our bake for LODs is also very important, since a lot of the time when we see a weapon in-game, it will be from a certain distance. We should focus on keeping a clean shading and avoiding gradients. Shading gradients will be very difficult to keep through the loading process, due to the big changes in geometry that our mesh will experiment. The flatter the shading and normal map look, the better our LODs will work. We must also, whenever possible, remember to bake small elements flat under their own geometry. When packing, we can also place some shells by hand that will make LODs look better. For example, a screw shell can go inside the hole it would be in the big surface shell. That way, when we remove all the geometry and we're left with just a shell, it will still look correct.